All right, welcome back. In this video, we're going to do Chapter 8, Section 1, Markov chains. Now, excuse the accent, okay? Markov, he's a good guy. But anyway, remember tree diagrams? Back in the day when we did tree diagrams? We're going to use those a little bit because they help us illustrate points. But in the grand scheme of things, we'll have nothing to do with tree diagrams in the long run because tree diagrams will get too darn complicated in the long run. We'll end up converting tree diagrams into matrices. Anyway, let's talk about what this chapter is all about. So in chapter 3, we studied Bernoulli processes, and in doing so, we created tree diagrams. The thing is, back then, each stage of the experiment always had the same probabilities. The probabilities of later stages did not depend on the results of earlier stages. So the difference here is it's gonna depend a little bit. The stages are gonna be quite different. So a Markov chain is a stochastic process which satisfies the conditions. One, at each stage, the result is one of a fixed number of states. I know this makes no sense to you right now, but it will eventually. Maybe if you watch this video to the end and then go back to the beginning and watch again, you'll be like, oh, now it makes sense. That's probably how it's going to work. 2, the conditional probability of a transition from any given state to any other state depends on only the 2 states. So let me give you an example. We're going to have an example coming up here. Yeah, let's just talk about this and I'll sort of emphasize what that was all saying. So a freelance computer worker, okay, or a computer network consultant, whatever, is employed only when she has a contract for work. And each of her contracts is for 1 week of work. So she's a freelancer. She's either on any given week, she's either employed for that week or she's unemployed for that week. And her record supports the following assumptions about the conditional probabilities. So if she is employed this week, the next week she will be employed with the probability of 0.8 and unemployed with the probability of 0.2. So again, she's only contracted for a week, so there's no guarantee that she'll have a job next week. But because she is under contract this week, her probability is a little higher that she'll find another contract next week, if that makes sense. But if she's unemployed this week, then next week she'll be employed with probability 0.6 and unemployed with probability 0.4. So if she's unemployed this week, again, it doesn't guarantee that she's employed or unemployed next week. We don't know. But the probability of her finding a contract is 0.6 for next week. So, 0.6 probability that she'll find some work next week, but 0.4 probability she won't. So this makes sense, right? Our freelance computer network consultant, if she's employed, she has a pretty good chance of getting another contract next week. But if she's unemployed, her chances of getting a job next week are a little bit slimmer. And this could vary from week to week to week. If I ask you the question, what's the probability she'll be employed 5 weeks from now? Well, that tree diagram that we're planning on drawing can get really, really chaotic because you have to do it for 5 branches. And we have no idea because it's not going to be 0.8, 0.2, 0.6, 0.4. We'll see what it gets out to be. But this is where matrices in the future will come in. We'll work on a matrices as we work this problem out. But let's start with the tree diagram because the first question is asked, she's employed this week. Find the probability she will be employed 2 weeks from now. So a tree diagram is simple enough because we only have to look 2 weeks in the future. So let's just make a quick tree diagram to sort of see what's going on. So the problem says that she is employed this week, so we know that. So the probability that she is employed next week is, what did it say, 0.8. And then the probability of her being unemployed next week was 0.2. So this is 1 week into the future, right? This is 1 week, and then this will be 2 weeks. Now, if she's employed after 1 week, then the probability of her being employed again here would be 0.8. And the probability of her being unemployed here, again, would be 0.2. Because remember, if she's employed, it's a 0.8% chance, not 0.8%, but 0.8 probability she's employed again, 0.2 she's unemployed. Now, if she happened to be unemployed after 1 week, then the probability of her getting employment on week 2 is now 0.6, and the probability of her being unemployed week 2 is 0.4. So there's your tree. So I believe, let's look at what the question was asking again. The question was asking, find the probability she will be employed. 2 weeks from now. So all we got to do quickly is run the math. And if you do 0.8 times 0.8, that's going to be 0.64. 0.8 times 0.2 would be 0.16. And we're not really concerning with ourselves with that one because we're focusing on the employed parts, but just go ahead and get the number anyway. 0.2 and times 0.6 is 0.12, and 0.2 and 0.4 is 0.08. So the unemployed percentages are, or probabilities are 0.64 and 0.12. So add those together to get a total probability of employment, and 0.64 plus 0.12 is 0.76. So the probability that she'll be employed 2 weeks from now is 0.76, 76% chance. Now, of course, you can see where the complication comes if I ask you 5 weeks, 10 weeks, etc. But matrices are really, really useful to make that a lot easier to find. So let's talk about matrices real quick. Or is it coming up? It's coming up. We'll talk about matrices coming up. All right, transitions. Let's talk about, I guess this is what the matrices is all about. Each problem we discuss has a certain number of states that concern us. In example 1, we talked about a network consultant just now who is in one of 2 states, either employed or unemployed. Now, the most important thing that we're interested in is the transitions, whether she's employed to employed again, employed to unemployed, or she's unemployed then going to employed, or she's unemployed and then stays unemployed. And now, so from week to week, the probability that she goes to a different state or remains in the same state is very important information that we need to have. Transition diagram. So you saw it briefly because I skipped ahead a moment ago, but it's a concise way to illustrate a problem states and a transition between them. So these are kind of fun to draw, in my opinion, honestly, just because it's kind of like doodling in a way. But anyway, so for example 1, our person was employed or unemployed. Now, the probability from being employed and then staying employed, so notice how I've kind of made a little loop back to myself here, that was 0.8. But from being employed to unemployed, what did that say? Employed to unemployed was 0.2. Now, from being unemployed and staying unemployed was 0.4, and going from unemployed to employed was 0.6. So if you're wondering where those numbers came from, you can scroll back right here. It's just this information right here. So employed to employed was 0.8, employed to unemployed was 0.2, unemployed to employed was 0.6, and unemployed to employed was 0.4. If I have to say employed one more time, it's going to suck. All right, here we go. So anyway, let me make a better version of this. That's not what I wanted to do, but it's cool. So there you go. That's a prettier version of what that would be. So remember, employed to staying employed was 0.8, unemployed staying unemployed was 0.4, and then the transitions from unemployed to employed or employed to unemployed. Anyway, that's just the information was given to us. It's just look, we made a sketch of it this time. Instead of writing it down, we made a picture. Voila. It looks great. Markov property. So this is where the matrices are beginning to come into play. So if a system is in state I, so you can think of this as being, let's say, employed. So for being in a specific state, like I said, like employed, on one observation, then the conditional probability that it is in state J, which can be unemployed, and the next observation depends only on I and J and not what happened before the system reached that state. So whether she was, is employed and going into unemployed, that has nothing to do with what her work was last week. It only matters what's this week and next. It's not going to make a difference what she was doing last week. That if she was employed last week or unemployed last week, that has absolutely no influence on the probability of right now of her, being employed to unemployed or whatever the situation is. So it's very important that we remember that the past does not concern us at all. It's really only the here and now where we are now and what we're going to that concerns us. So this probability Pij thing, this is where our matrix is going to come in from. It's probability of making a direct transition from I to J. So let's call, do I have room on the next slide? I do. Here, I'll just do it on this slide. So let's just say this. So let me show you how to make a matrix now from our problem. Let's say employed was, we'll call it state 1, okay? And unemployed is state 2. So in our matrices, right, our A11, this is saying, I usually make these lowercase, so let's just keep it lowercase. This is saying from employed to employed, right? Because we called employed 1. So the probability, here, I'll just go ahead and write these all in. 1, 1, A1, 1, 2, A2, 1, A2, 2. So this first spot is the probability of going from employed to employed again, which we just noted earlier was from employed back to employed again was 0.8. So 0.8 goes there in that matrix. This spot is being employed to unemployed. So being employed to unemployed was 0.2. So 0.2 right there. This one is from being unemployed to employed, which from unemployed to employed was 0.6. And then this last one is being unemployed and then staying unemployed, which as we saw from earlier, unemployed and staying unemployed was 0.4. So our matrix for that first problem is this, 0.8, 0.2, 0.6, 0.4. And now making that matrix is important because, of course, coming up, we'll deal with problems where making the matrix is part of what we're going to do, and it'll help us much quicker. I don't know. Anyway, quicker. I'm trying to find another word, but it's not working. A fast way of solving these problems. So we just mentioned this. This was me making the matrix. Calling E employed 1 and unemployed 2, and then filling out the matrix as such. So we'll cut that out. Find the transition matrix described in example 1. Well, we already did that. The 0.8, 0.2, 0.6, 0.4. So we're going to go ahead and skip along. Example 3. A tree diagram for a stochastic process with 2 states is shown below. Determine whether this is a tree diagram for a Markov chain. How can you tell? Well, remember the probabilities, from being employed to employed was always the same. It was always 0.8, right? Well, think of A as being employed here and, B being unemployed. Well, A to A is 1/3, and then A to A again is 1/4, and A to A again is 1/5. See how those probabilities are changing? That's not supposed to happen in a Markov chain. Markov chain, these probabilities are consistent throughout. So I'm doing the same exact transition. I'm in A and I'm staying in A. And if that's the case, then the probability should always be the same. Like if I'm employed and then I'm going to be employed again next week, that probability was always 0.8. So you can't change those probabilities. So the fact that I see different values here, 1/3, 1/4, 1/5, that tells me this is not a Markov chain. It's probably a nice scenario of some kind, but it's not a Markov chain. So we wouldn't use any of the math that we're doing now to try and solve that. All right, moving on, example 4. The service specialists of Metroburg Heating and Air Conditioning Company make their calls with a fleet of radio dispatch service trucks. Established procedure is that when a call requesting service is received by the office, the dispatcher sends the next available truck to respond to the call. One of the service specialists keeps records of his service calls, and his data are summarized in the table. Formulate this situation as a Markov chain, find the transition diagram, and the one-step transition. Okay. So let me break down what this kind of chart is saying for us. So there's 3 states the driver can be in. The driver is either in east, central, or west. Okay. So if he's in east, then the probability his next call is also in east is 50%, which I guess we're going to change it to 0.5, right? If he's in east and the probability of him going to central for his next call is 0.4, and if he's in east and the probability of going to west is 10% or 0.1. Okay, so that's kind of how this is broken down. It's telling us where he is right now and then the probabilities of where he'll be on his next call. Okay, you got me? Look at this because I have to go. Nope, I guess I can't. I guess I'll have to squeeze it in on this screen. But we are going to make a transition diagram. So our transition diagram is going to have 3 states: east, central, and west. Now, I guess I'll just leave them as this. I was going to change them to numbers, but I guess we can leave them like that. So from east back to east is 0.5. So I'm going to draw a little loop back on itself. East to east, that's 0.5. East to central is 0.4. So east to central, draw a little arrow, 0.4. And then east to west is 0.1. East to west is 0.1. Now I'll do the central. So central to east is 0.1. Central back to central, so a little loop back upon itself, if I can draw a little arrow, is 0.6. I know this looks kind of crappy, but it's fine. And then central to west is 0.3. All right, and then lastly, west to east is 0.3. West to central is 0.6. And this is looking terrible, but it's cool. It'll probably look better when I do it in class. West to west, so west back upon itself is 0.1. So there's your very pretty transition diagram for you. Okay, so anyway, we could probably make a matrix of this as well, but it's not what the question asked. So I guess maybe we'll do it in the next section. But that's going to cover it for 8.1. We're definitely going to be looking at these same examples again in either 8.2 or 3, so it will come back up. But at least you have a general idea now of what we're dealing with. We're talking about being in a certain state and transitioning to another state, and the probability of that occurring, or remaining in the same state, but the probability of that occurring. And the fact that those probabilities are always the same makes a big deal difference as well. So, yeah, we're going to do a lot more with this coming up, but that's going to be it for this video. I'll see you in the next one. Bye.